Having seen invariants in use quite a few times, we now come to monovariants. As we said above, these are quantities or more general things that only change in one direction. So numbers that only grow or numbers that only decrease. And we're going to see them in use a few times. The first application is a very basic result that is being used in, for example, in computer science a lot. And it's not very difficult, but it's worthwhile to see this proof, even if you've seen it already. So here is the definition. We say that an n-tuple of numbers, let's say real numbers, is weakly increasing if a1 and less or equal to and so on less or equal to an. That's what you would expect. It's like a discrete weakly increasing function. And secondly, let a1 and so on an be an n-tuple of real numbers. Two entries ai and aj of this n-tuple with I less than j are said to be out of order if ai is bigger than aj. So out of order basically means that they're not weakly increasing. So if the tuple is weakly increasing, it has no two entries that are out of order. So for example, in the 3-tuple 1, 3, 2, the second and third entries are out of order. And for another example, in the 4-tuple 3, 2, 2, the first and the third entries are out of order, and so are the first and the second entries. But now the actual exercise. Let n and n, you start with an n-tuple a1, a2, and so on, an of real numbers. In one move, you are allowed to pick two adjacent entries ai and ai plus 1 that are out of order, if they exist, of course. So in this case, this means they satisfy ai is bigger than ai plus 1 and swap them, which of course makes sure that they're not out of order anymore after the swap. Prove that after at most n choose two such moves, the n-tuple will be weakly increasing. So here is an example, and I'm just going to do the moves in place. So let's start with a reasonably wild 5-tuple, which you see is not weakly increasing, very much not weakly increasing. Now we can pick any two elements, any two adjacent entries that are out of order, for example, 4 and 1, and swap them. Okay, so it's 1, 4. Still not weakly increasing. 5 and 3 are out of order, so you can swap them and get 3 and 5. 5 and 2 are not out of order, so you can swap them and get 2 and 5. 3 and 4 are out of order, so you can swap them and get 3 and 4. 4 and 2, swap, you get 2 and 4. 3 and 2, swap, and you get 2 and 3. And now the n-tuple has become weakly increasing, so there is nothing out of order anymore. It's a fairly reasonable statement. It basically says that you can sort a bunch of numbers by just repeatedly taking two consecutive ones that are not in the right order and fixing their order. Well, it's intuitive, but this is not a proof yet, because in theory, when you swap an out of order pair, some other pairs might also become out of order. And the whole idea is to make sure that this doesn't really happen, or at least the number of out of order pairs does not grow, it only decreases. So this is where monovariants come in. So when I say n-tuple in this discussion, I will always mean n-tuple of real numbers, or basically n-tuples of anything that you can compare. If you know this notion, n-tuples of elements of n-tuple of elements of a totally ordered set. But let's just pretend they're numbers. Now, an inversion of an n-tuple, a1, a2, and so on, an, means a pair ij with I less than j and ai being bigger than aj. So the inversions correspond to the out-of-order pairs in the n-tuple, but they're not literally the same, because an inversion tells you the positions. So an inversions consists of the positions of an out-of-order pair. So for example, in the 3-tuple, let's call it 6, 9, 4, 5, the pair 6, 9, no, the pair 9, 5 is an out-of-order pair, and the corresponding inversion is 2, 3, because the 9 and the 5 are in positions 2 and 3. So we don't call 9, 5 the inversion, but we call 2, 3 the inversion. And likewise, the pair 6, 5 is out of order, with the corresponding inversion being 1, 3. The reason why I'm working with the positions instead of the entries is that if I have a tuple like this, with inversions, it's clear how many there are. There are 2. There is this 3 before this 2, and then there is this 3 before this 2. But if I was talking about the pairs of entries, they would both be 3, 2, and you might easily confuse them for being one and the same inversion, which is not the case. So inversions are, in this case, they're less ambiguous, which is why I'm using them. Now, also, the inversion number of an n-tuple is defined as the number of inversions of this n-tuple. Duh, not very interesting, but now we can easily say what we want. Here is a crucial claim. Every move decreases the inversion number of an n-tuple by 1, and I mean by precisely 1. Once this claim is proved, we will be almost done. Because if we know that every move decreases the inversion number by 1, but in the beginning, the inversion number was at most n choose 2, because any inversion is such a pair ij with I less than j, and the total number of such pairs is n choose 2. You cannot have more than n choose 2 inversions. And then every move decreases it by 1. So if you have more than n choose 2 moves, it has been decreased so often that it's negative. But an inversion number cannot be negative. It's still a number of some things. So you cannot have more than n choose 2 moves. Okay, but anyway, I will formulate this once we're done with this proof. So how do we prove claim 1? And here, I think an example is maybe more useful than more blabber. So I'm going to draw on the screen now and show you an example of a tuple. So here is a 5-tuple. 4, 1, 5. Let's do 2 and 3. So how do we find its number of inversions? An inversion is just a bigger number before a smaller number, not necessarily consecutive, not necessarily adjacent, but just somewhere before, so somewhere to the left. So for example, this 4, the 4 at the beginning being smaller than the 2, that's an inversion. So let's represent this inversion by drawing an arc from the 4 to the 2. Let me also draw the other inversions. 4 is before 1, 4 is before 3. So 1 is not before anything that's smaller than 1 because there is nothing smaller than 1. But 5 is before 2 and 3. And that's it. These are all the inversions. And now, let me take these two. So let me make a move. And I'm going to do these two numbers. These are two consecutive adjacent numbers that are out of order. So I can move by swapping them. So I get 4, 1, 2, 5, 3. Okay, now what happens to the inversions? So this inversion, the 4, 1 inversion, this one, that stays an inversion here after the move, because neither 4 nor 1 has moved. Now the 4, 2 inversion, what happened to that? The positions have slightly changed because the 2 has moved, but it's still there. There is a 4 and there is a 2. So the inversion has changed the pair of entries, but the pair of entries is still out of order, so we still have an inversion. For 3 again stays in its place because neither 4 nor 3 has moved. 5, 3 is still there, but the 5 has moved, so it's now here at the bottom, at the right. And finally, what happens with the 5, 2 inversion? That one is gone. There is no 5, 2 inversion anymore because I've swapped them and now they're no longer out of order. So you see, it's not like the inversions have literally stayed the same, but a bunch of them have slightly shifted, or rather they have been stretched or they have been compressed. One has been lost, otherwise they're still the same. And this is where I want to leave it for this video, but see the notes for a detailed proof. All right, and now let me finish what I promised. Let me explain how this how this leads to the answer to the exercise. So the inversion number of an n-tuple is always an integer greater or equal to 0 and less or equal to n choose 2, because there is only n choose 2 this kind of pairs, and this condition can only decrease the number. So claim 1 shows that each move decreases it by 1. Thus, if we made more than n choose 2 moves, then it would decrease by more than n choose 2 times 1, so more than n choose 2, which is impossible because it has to be an integer between 0 and n choose 2, since it needs to remain an integer between 0 and n choose 2. So we cannot make more than n choose 2 moves. Thus, after at most n choose 2 moves, we will have an n-tuple to which we can no longer apply any moves. But what does it mean we cannot apply any moves anymore? It means that no 2 adjacent entries are out of order, because if 2 adjacent entries are out of order, you can move. You can swap them and that will be a move. But this is just saying that this n-tuple will be weakly increasing. This here. And that means we're done.